All right, here's the solutions to the multiple choice section of the recent methods task, I suppose we'll call it. So what I'll do in this video is work the MC questions. In the next video, I'll work the short answer questions. So let's see how fast we can knock this over. All right, so question 1 says, what's the range of this function? So what we've got is the root function here. So I think this is quicker to just sketch it rather than do it on the calculator, even though it's tech active. So this is the root function going -4 units that way and -1 unit down, or 1 unit down. And it's going to flick like so. And what we've got here is a restricted domain. So it's going to be from 0 onwards. Is the domain. So all I need to know is the range from there up. So to work that out, I'm going to go f of 0 equals root 4 take 1, which is 2 take 1, which is 1. So that coordinate there is y equals 1 up to positive infinity. So what we've got here is E. All right, Q2. This one here, what we're looking at is some sort of a parabola that's invertible from -infinity up to A. So I suppose what I'm going to do with this one is work out the turning point. And again, I think this can be done pretty quickly on the calculator, by hand rather than the calculator. So all I'm going to do is throw it into turning point form. So x squared plus 2x plus 1 squared, take 1 plus 3. So I've just completed the square on that, which is x plus 1 all squared plus 2. So it's going to be -1 and 2 is the turning point. It's an upright parabola like that. So they want it to go from -infinity all the way up to and including this value here. Okay, so that's going to be where the function is 1 to 1. After that, it's going to be not 1 to 1 anymore, which means that when I inverse it, it's not going to be a function. Okay, and what I'm saying there is, imagine we've got a full parabola there. When it gets inversed, it's going to look like that, which means that for 1x value, there's 2 y values here, which means this is not a function. Okay, so we're looking for when it has an inverse function. So it's going to be up to and including -1. So A would be a value from -infinity all the way to -1. There's our answer there. This one, the maximal domain of this function here is a bit tricky, this one. My suggestion on this one is to go to the calc and have a look at this. I'm pretty sure what this function looks like, but I'm not 100% sure. So what we're going to do is graph. So I'm going to go shift divide to have a look at this thing. Not shift divide yet. I'm going to go shift hat to root it and shift divide x take 3, x take 6. All right, let's have a look at it. Yeah, so what it's going to do is basically root it up to there, and then it's sort of going to have kind of hyperbolic behavior, if that's kind of even a word. But what it's going to do is approach 6, but never actually touch it. So my thoughts are this part here is going to be from -infinity all the way up to and including 3. Now, why including 3? Well, that will generate 0 here. 0 divided by anything will be 0. So it will accept that value. Union with, from here, it's going to be kind of asymptotic behavior tending towards x equals 6 all the way to positive infinity. All right, let's see. There it is. Okay, the range between 0 and 7. A lot of students for this one will jump on their calcs and bang in 0 and 7 as the endpoints, but that's not what you want to do with this. What you want to do is just do a quick sketch of it. So it's 2, 2 as the turning point. Now we're going to chop it at 0 and all the way up to 7 over here. Excuse the scale, but it does give you the idea that like this value here, 7, is going to be the max value and the min value is going to be the turning point. So it's absolutely going to start at 2 as the lowest point and it's not going to be the value of 0. So many of you made a mistake on this one. I bet you just subbed in 0 and 7 into f of x. But make sure you go and have a look at the function first, or plot the function first, to work out what the range is going to be. So to answer this one, I'm simply going to sub 7 into this. So let's see if we can do it by sight. 7 take 2 is 5, 5 squared is 25, doubled is 50, 52. That's going to be 2 to 52. And that point there is not included because when I bang 7 into the function, it's not going to actually include its output. So it should be 2 to 52, which is A. All right. We're going to distance between points problem. We're going to use the distance formula, which is the square root of. Now what we're going to do is work out the difference in y values. So negative 3b take b is negative 4b, and we're going to square the result. Plus, so we're just using Pythagoras' theorem here, really. 2a take negative a, which is 3a all squared. D equals root of, now negative 4 squared is 16b squared plus 9a squared. Okay, inverse functions. So this is a linear from reals to reals, so it's going to look something like that. This is a parabola from 0 to positive infinity. So that has an inverse function because it's still one-to-one based on the domain restriction. This is the inflected parabola, inflected cubic, and that absolutely has an inverse because it's one-to-one all the way through. This is the top half of a circle, this one here, so that will be our answer. That's going to be the top half of a circle with a radius of 2, okay? So that one does not have an inverse function because it fails the horizontal line test. That is, for this x value and this x value, we produce the same y value, which means when it's inversed, I'm not quite sure what the inverse is going to look like, but for these x values here, the inverse will produce, or these two x values, well, what's going to happen? Anyway, that's beside the point. It's just one-to-one. It's not one-to-one. Oh my goodness. Okay, stay with me. It's not one-to-one, therefore that is our answer. And just to confirm it, that's a hyperbola up 2 units. So up 2 units, and it's negative. So that's going to be like that. Okay, and that certainly is one-to-one. Okay, this one here, for this function here, for the real positives to that, the inverse will be. So let's have a quick look at this. Negative 5 is not included because it's real positives, which means 0 to positive infinity. So when I put 0 in, it's going to be negative 5. Positive gradient means it's going to go up like that. So it's negative 5. So the range of this function will be negative 5 to positive infinity. Now, why am I interested in the range of this? Because the inverse will have a domain. So dom f negative 1 will be negative 5 to infinity. So the range of the original becomes the domain of the inverse. All right, let's see if we've got a winner. So all of these are candidates. This one's not actually. So it could be D or E. Now, which one's it going to be? All right, so we don't have to do it all officially. We can just quickly go x equals 3y. So I'm not so worried about notation because it's just a multiple choice. X plus 5 on 3 equals y. I think it's this one, 1/3 x plus 5 equals y. Yep, it's D. Okay, now what's this one here? So what we're doing is the product of functions here. So the way we do this one is we consider the maximal domain of h of x, which is made by multiplying the two functions together. So let's have a look at the two functions individually. So this is x negative 3, that's the root function. This is also the root function. I'm just going to rewrite it. Negative x take 2. So 2 units to the right and flicking that way. So h of x is going to have a domain where both of them actually have a number to multiply each other by. So notice how here, like if I sub in, say, 3, the only function that's got a value is this one here, which is g of x. But g of x doesn't have anything to multiply because f of x isn't true there. So it's actually only going to be able to multiply the functions together between these two values where they both can produce a value. So it's actually going to be between -3 and 2 where it can actually produce a resulting function. So therefore, that is going to be the domain of h of x. Okay, what's this one? Okay, what we've got here is two functions. These are pretty tricky, these ones. So what we want to do is do this composition. So we're doing f compose g. Okay, now for this to work, what happens is g of x will produce a range of functions that has to fit within the domain of f. So what comes out of g of x has to fit within f of x. Okay, otherwise what will happen is if g of x can produce a value that f of x can't take, the composition is not going to work because f of x is going to reject it, saying, no, I'm not having this one. So what do? We need to note that for the composition to work, the range of g, which currently is a comma, no, it's not. The range of g, let's go with this, must be a subset of the domain of f. Okay, so we know the domain of f, which is 0 to infinity. Now what we need to get is the range of g of x. So that's a linear function, goes through 1, like so, to positive infinity. And really what we need to do is force this a value here to be 0, okay? And that's like saying to g of x, hey, for what values of x are you going to be 0? Right, that's what I want to find out, really. I'm going to go 0 equals x plus 1. X is equal to -1. And that's actually going to be my value of a. So the range of g will be, if x is negative, if a is -1, will be 0 to infinity, yeah? All right, so it's that value of x, or that value of a, that's going to do it for us. So a must be -1 for this to happen, okay? So again, just to go back on what I've done there, because I think this is a little confusing, what we've got is the rule for composition is the range of the inside function must be a subset of the domain of the outside function. So we know the domain of the outside function is this. So what we need to do is make the range of the inside function a subset of it. So it has to be from 0 to infinity. In this case, it's the least value. So we want it to fit in, with as large domain as possible. So I need to work out for what value of this, I need to work out, hey, I need to make a 0. So what value coming out of it? So 0 equals x plus 1. Yeah, tricky one, that one. See if you can work that out and redo that question yourself. Okay, the values of k that will give the equation has at least one. The wording doesn't really make sense, but the question does, and most of you, I think, know where this is going. So we want at least one real root. Okay, so one real root will happen when we've got a discriminant equals 0. We know 0 equals the discriminant, which is b squared, so it's 36. Take away 4 times a times c. 0 equals 36. 4 times -3 is -12, plus 12k. Negative 36 equals 12k. K is equal to negative 3. There we are. Okay, some of you guys use long division on this one. No way. Okay, so what you want to do is define f of x equal negative x cubed take away 2x squared plus x plus 3. And what we're going to do is use the remainder theorem. And the remainder theorem says basically that if you put, so if this is a function here, if I put p of negative a half, so the way I consider it is when that is equal to 0, x is equal to negative a half. So when I put that negative a half into the function, what the remainder theorem will do is, funnily enough, tell us the remainder. So let's do it. Negative a half. 17 on 8. 2 and 1/8. There it is. 2 and 1/8. Function f of x has a stationary point at I presume at what x value? All right, so yeah, let's just find out. Define x equals x cubed, take away 12x plus 5. Now what I'm going to do is diff the function for x. Well, the default's x, so just a quick thing there. Note that it'll still diff it for x automatically, but it's a good habit to put comma x in there. Now, what I want to do, that's the derivative function, and what we want to do is say, hey, derivative, when are you equal to 0? What value of x are you equal to 0? So ANS means that thing there, the derivative function, when are you 0? And it says I'm 0 at 2x values, x equals negative 2 and x equals 2. So I can only presume it's that one there, because it's not asking for coordinates or y values. Okay, this one here, f of x equals that, f dash 3 equals 73, a must equal. All right, so for this one, I'll define my function again. Here's what I'm going to do, solve. No, I'm not. I'm going to diff it. Okay, now I've got my derivative function. Now what I'm going to do is the derivative with x equals 3. So I'm doing f dash 3 is 69. Ooh, that's naughty of me. Okay, so there's a little mistake in what I've done up here. When I've written the function out, I have used from the keyboard, instead of using var, I've used ABC, which is actually okay as long as I know to put a multiply between those. All right, that should sort it out. Okay, so I've diffed it, which gave me that derivative there, which looks good. And I've put x equals 3 into the derivative, or done f dash 3, which is a plus 69. And then I'm going to go solve ants, or the derivative with x equals 3 in it. Solve ants equals 73 for a. Now hopefully you can see that the answer is going to be 4 by sight, but I just wanted to use a calculator. All right, 14. Easy. Derivative of this is 4x. Take 9x squared. Yeah, that's it. 4x. Take away 9x squared. Yep. Okay, after all the cool stuff that we've been doing, just that. Anyway, min value. What's the quickest way of doing this? I think the quickest way is just to complete the square by hand. You could use fmin on the calculator, type in the function in fmin, but yeah, I can complete the square fairly quickly on this. We're going to go negative x squared take 6x take 4. Now let's complete the square. Halve it is 3, square it. Take 9, take 4. Right, so it's a parabola. It's going 3 units to the right, 13 up. It's inverted. So the maximum value, I think I might have said minimum value. Maximum value going to be 13. I'll make sure you got this program on your calcs as well by the end of, well, soon anyway, before the SAC. But use TPT, tells you the turning point of it. You guys don't have that yet, but that's another way to do it. I could use Fmax rather. Interactive, calc, Fmax, function, variable. You can tell it. That's a pretty wide search area, but it'll go find it for us. Maximum value is 13 at x equals 3. So there's 3 ways, or 3 different ways of doing the same problem. All right, the equation of the tangent to this at, all right, that's easy on the calculator. So go calc, line, and tan line. All right, our expression is the function 3x take 2 at x is equal to -1, x take 3. Average rates, okay, not to be confused with average value of a function. I think these are best done with function definitions. And what we're going to do is just use y2 take y1 over x2 take x1. So I'm going to do the y values, which is f of -2, take away f of 0, all over -2 take 0, which is -2, and we get 2. Oops, wrong side of the stylus. Okay, grading of the chord, probably pretty quick by hand, but I'm prone to making some mistakes, so let's just bang this one out on the calculator as well. So gradient of the chord is given by simply the gradient formula. So I'm going to do f of 1 plus h, take away f of 1, all over 1 plus h take 1 is just h. There it is there. Let's hit a simp on this, so we'll see if it simplifies down. Aha, there it is. All right, so don't forget that simp. If you think, yeah, you're going right and your calculator produces that, hit that simp button and see if it will actually simplify it a bit further. I think on your papers, this one was corrected. It says G-2. So probably could just chain this by sight, but f of x equals x take 8 to the 4. Diff f of x gives me my derivative, and I want to bang 2 into the derivative. So the ants or derivative function with x is equal to 2 is 160. Okay, always a bit of a trap, this one. Oh, what a good question, Ms. Cowan. All right, so this is pretty good. All right. What you don't want to do with these ones is simply just place it in there. There's always some sort of factor thing that you can do with this thing. Now, let's just see what 9 take 12 plus 3. Looks like it's going to give a divide by 0. Oh, undefined. So it looks like it's undefined, but actually what we'll do is we'll just factorize this perfect cube here, okay? So I'm just going to go factor, or you should probably get in the habit of using R factor. Now, where to get a factor, because I've got a keyboard, I'm typing it in, but factor can be located in transform and factor, R factor. All right, so we're going to go x cubed, not capital x cubed, take 27. All right, probably is tempting just to write that as like x take 3 all cubed or something like that, but anyway, it's not. So it's going to be, now again, I'm not using the correct notation, but I'm going to write x squared plus 3x plus 9 all over x take 3 over this thing here, 1, 3, x, neg, x take 1, x take 3 is the factorized version of that. That cancels with that, and now it's game on. So let's whack the 3 in there. 9 plus 9 plus 9 all over 2, 27 on 2. The calc does limits as well, but it's pretty cumbersome and it's probably quicker by hand. Limits are here as x approaches 3, and you're then simply going to type in your function x cubed take 27 all over x squared take 4x plus 3, 13.5, which is 27 on 2. Okay, the equation of the normal to the curve with the equation at x equals a. Alright, let's define this. F of x equals 2x to the 3, take 3 times a times x squared plus 5. Why don't we find out where the stationary points are? Diff. So that's the derivative function. Solve the derivative function equals 0 for x. Aha, okay, that's it. All right. So what's going to happen is it's always going to have a stationary point at x is equal to 0 and x is equal to a. All right, this is a cool question. All right, so I'm not 100% sure what the function is going to actually look like, but I know that it's going to have a stationary point at these 2 points. So at 0 and at a. So for argument's sake, it might look like this. Stationary point at a, stationary point at 0. In which case, the gradient of at the stationary point is always going to be 0. Which means that the equation of the normal to the curve at that stationary point is, the normal, remember, is perpendicular to the tangent. That's this. Right, and what will happen is this is always going to be the line x equals a. So that's your answer there. Now, what I'll do, I'll pull this up here and show you what I mean. So let's graph the function y equals 2x cubed. I go 3 times a times x squared plus 5. All right, here it is, and you'll notice that here a is equal to 1, and that's one of my stationary points. So no matter whatever a is, this will be the stationary point. And let's whack in a tangent. So if I put in a tangent, well, let's do x equals a. So we're going to plot that line. So you'll notice here that whatever the value of a is, it's going to have this vertical line as a normal, because this turning point here is always going to be the value of a. So no matter what I vary it to, the normal will always have that equation. All right, I reckon that's a pretty tricky question. Okay, transformations. What we've got is this going to this. So start with from y equals x squared to y equals 4 take x take 3 squared. This is our image. So what I want to do is pair them up. So I've got to get this one ready for it. Over -1 equals x dash take 3 all squared. All right, so what I'm going to do now is say y is equal to y dash take 4 all over -1, and x dash is equal to, not x dash, x is equal to x dash take 3. All right, now what do we solve for? Well, let's check it out. So x comma y maps to, that's x dash, that's y dash, right? And these are the transformations. So what I want to do is write in the transformations there, okay? So that means I need to make x dash the subject and y dash the subject. So x dash equals x plus 3, that's this one here. So x plus 3 is x dash, and -y plus 4 equals y dash. -y plus 4. All right, so let's just see what we've got. Let's have a look. So this is a reflection in y, a reflection in x rather, reflection in x, translation of 3 units parallel in the positive direction, that's that, and a positive translation of 4 units parallel to y, that's that. Yep, it's E. Okay, what do we got? F of x is that, and what it's been doing is sent b units in the positive direction. All right, how's this going to work? All right, well, let's see. If this is -b, what I'm going to do is shift this point b units to the right, which will mean it ends up here, which means this, which was at 0, is going to go b units over, and this is going to be out here, which is going to be 2b units. All right, so that's what it will look like after it moves b units to the right. It's also got a dilation factor of a from x. So this point here will be 0, 1 at the moment. And when I multiply, so dilations from x change y. So this value here is going to be dilated by a factor of a. So it's going to become 0, a. This one is going to become, what is it? 2b, -a. 0a. Yep, it's this one. Graph whose equation is this. Which one of the following represents the graph whose equation is this? Right, so this negative means it has been reflected in the x-axis. So let's just do that first of all. So we're going to get 1 and try that again. That's pretty ordinary, but you get the point. Then what happens is it's moving, so that's x plus 1. It's going to move 1 unit to the left. So here's -2, so it's going to be here. And well, I can already see it's got to be this one, I think. Hang on, what happens to it? It goes 1 unit up. So that's going to be the coordinates -1, 1. When it moves 1 unit up, it's going to be -1, 2. That's the only one it can be. Okay, pause there, and I'll hit the short answer in a sec. All right, let's do this short answer now. So what we've got is a function f of x down here, and we want to dilate it by a factor of a half from y. Okay, so remember f2x is a dilation by a factor of a half from y. So what that's going to mean is this coordinate here, which was originally -4, -2, is going to become half from y, -2. It's going to go to this point here. This one here, so label all important points clearly. This one here is going to be half from y. So it's currently at 3, it's going to be 1.5. So that's going to be -2, -2. This one's going to be 1.5, 3 on 2, 2. All right, when I dilate this from y, it's going to stay in exactly the same spot. So my new function will be that. Right, excuse this, girls. I'm on a pad. I'm not actually drawing on this screen physically. I'm on a pad next to the computer, so it's hard to actually get that to go through the point. Right, this one here says grab me the inverse, please. So this point was originally -4, -2. That means when we swap x and y, that we're going to plot -2, -4. That's down here. And this one here, where are we? That's 3, 2. That's going to be 2, 3. It's going to be up here. All right, let's try to hook them up through there. Make sure you label all important points clearly. I don't know whether they want x-intercepts. I can't really because, oh yes I can. That one. So that's the y-intercept, which will become the x-intercept. So my function should have gone through 2. So disregard that. So that's going to be 0, 2. This one here is going to be swapped values. It's originally 3, 2, 2, 3. And the y-intercept will be the former x-intercept. So that will have to be down a bit lower. All right, so fix up that shape or make sure your shape looks okay. I don't know exactly what that value is, but at least it runs through what should be the value down here. And the coordinates of that endpoint are -2, -4. Okay, is divisible by that. So that means that 0 equals p of 2 equals 8 plus 4 plus 2a plus b. 2a plus b equals -12. But when divided by 3 gives a remainder. So again, using remainder theorem, 5 equals p of -3 equals -27 plus 9. Take 3a plus b. -32, -23, I think. Okay, there's 1, there's 2. Yeah, probably could do this by hand quite easily, but it's getting late. 2a plus b, -23 equals -3a plus b, a comma b. Yeah, I don't remember that being the answer. What have I done wrong? All right, yeah, there's my mistake there. So add 27 to both sides gives you 32. 32 take 9 is +23, not -23. All right, let's just fix that up. That's it. So A equals -7, B equals 2. All right, find the coordinates of the point on the parabola at which the tangent makes this angle with the x-axis. All right, so for that, what we want to find out is m equals tan theta, tan 5 pi on 6. So back onto the unit circle, there's 5 pi on 6. Tangent is going to be negative, m equals negative. That is on 6. That is going to be -1 on √3. I'm using those exact values from last year. So I want to find out when the derivative of this, what values of x does it have a gradient of this. So I'm going to go -1 over √3 equals this derivative, 2x take 2. Probably not going to do that by hand. Let's define my function. Let's do a diff, solve it. Hey, when are u equal to, so when is the answer or the derivative function, which is this, equal to -1/3. What value of x? That one. And it wants the coordinates. So what we're going to do is get the y value. So to do that, I'm going to go f of this nasty looking thing here. Slam it in. Come on. In you go. That looks prettier. How's that? Anyway, it is. Y equals -191 over 12. -√3 on 6 plus 1, comma, -191 on 12. Almost there. All right. The old simultaneous problem. All right, so what we're going to do is we have no solution, which is m1, same gradient, different y-intercept. Okay, so let's transpose these to make y the subject. For the first one, y equals negative k plus 3x plus 12 over k over k. Second one, y equals k take 1, negative k take 1, x over k take 3 plus 7 over k take 3. Right, so let's pair up these gradients. So it's when m1 equals m2, negative k plus 3 all over k equals negative k take 1 all over k take 3. Okay, so let's solve that thing. Okay, so that's k equals 9. Now we're going to pair up these things here, which is 7 over k take 3 equals 12 over k. Going to do that on the calc as well. Oof. K is equal to 36 on 5, but this is actually when they're not equal. So not. All right, so the value of K for which the simultaneous have no solutions is when K is equal to 9 and K is not 36 on 5. If it's 36 on 5, what I believe will happen is it'll be the same line. Yes, it will. Okay, what do we got here? We're going to consider this function here, invert it to find the inverse function. Right, so here is the domain. So what I want to do is find out the range of this function here. So how are we going to do that? Let's just draw it. F of x equals negative 3 take x on 2 plus 4. That's 4 up. So it's going to do that. It's moving left or right, I don't know which direction, it doesn't really matter. I'm just trying to find out the range. So the range is going to be negative infinity all the way up to and including 4. All right, now we're ready to invert. So what we're going to do is say let y equal f of x equals this thing here, 6 take x on 2 plus 4. We're going to say swap x and y. So x is equal to negative 6 take y on 2 plus 4. Now we'll do x take 4 equals negative root 6 take y on 2. 4 take x, and let's square it at the same time, equals 6 take y on 2. 2, 4 take x squared equals 6 take y. Y equals negative 2, 4 take x squared. So take 6 plus 6. All right, so there's my inverse function. We want f negative 1. So we'll go f negative 1 is a function such that it has a range of, or domain rather, of negative infinity to 4 inclusive, maps to the codomain, which is a set of all real numbers. F negative 1 x is equal to negative 2, 4 take x, ooh, I'm running out of space here, squared plus 6 plus. Had to write it. Okay, state the domain and rule for this. So they want us to do the composition. So let's do the composition. We're saying do it. So we're going to go f of root x equals, see where this one's going, root x all squared take 1. Now many students will just go, brilliant. This is square root squared is just x take 1, which will have a domain which is x is an element of all reals. All right, but that's what you don't want to do. All right, this is the true function composition. Okay, and this one here still means that even though this is a linear function, this is what it's based on. And so to that end, this is actually a composition where x is an element of 0 to positive infinity, because it's based on that. Okay, you can't just sort of go, oh, I'm going to square you, and now you're going to accept all real numbers, because this one will not accept all real numbers. G of s x. Okay, so this one, so for a composition to exist, the range. So what is? So I need to sort of see it to do it. So this is G f x, which basically says that it's going to accept values, pump them out. So the range of f has to be a subset of the domain of G. Now in this case it doesn't exist, so this is not going to be true. And let's have a look at the range of f. So the range of f, that's x squared take 1. That's that parabola there. So -1 to positive infinity inclusive of it is not a subset of the domain of G. Domain of G is 0 to infinity. So notice that this composition doesn't work because -1 is less than 0. So this does not fit into this, therefore it doesn't exist. Okay, last question. Ooh, okay. Okay, this is addition of ordinates. So what we're going to do is, I'm just presuming this is a really large dot, but I'm just presuming that this dot here is -2, 0. This one here is -2, 11. So what will happen when I add these ordinates together? It's going to stay in exactly the same spot, because that's 0 plus 11, which is 11. This one here is 0. It's going to go through here. So 0 plus whatever this value is here is going to be just that value. This is going to be what? -4. -4 plus 2 is -2. This one is going to be here. 0 plus whatever the value is. And what's that? 1, 2, 3. So that's going to be 1, 2, 3. It's going to be there. Function is going to terminate there as well. All right, let's see if I can draw this. Not bad. All right, so that's going to be the result of that composition, that addition of ordinates, addition of those functions. All right, so there's the solutions done in 53 minutes.